Hello, everyone, and welcome to a new session of Math Made Easy. In this session, I wanted to start doing some work with calculus, with differentiation to begin with. So I have in mind to do three things like a chain rule, related rates, and implicit differentiation, for example. And let's say we are going to start with related rates today. So what do we mean by related rates? It means that if I have two functions, okay, two functions say of x that change simultaneously and they are related somehow. We know the relation. And we tell you that x, for example, at some point in time is increasing or decreasing by a specific rate. At that instant, how does the other variable change? If so let's say related rates and then talk about it. Related rates. Let's take a very simple example. If I tell you y equals 3x, okay? And x changes, by how much does y change? Of course, here you don't need differentiation. You say, okay, if x increases by 1, then y increases by 3. If x decreases by 2, then y would decrease by 6. How did you know that? It's 3 times x, right? If you take the differentials, meaning if I take a small piece of x, call it dx, then 3 times the derivative with basically the derivative or the differential of x is dx and the differential of y is dy. So we say for every small increase or decrease of x by a minute amount, a very small amount dx, dy would increase 3 times as much. Okay, so what if y equals x squared? Okay, let's pick an easy number. Let's say if x equals 10, y equals 100. Let's take delta x or dx to be 0.01. By how much y would increase? I don't know. Well, let's see if I take the derivative of the right-hand side, I take the differential of that, I will get 2x dx. Notice I'm not taking dy with respect to x. No, a small piece in x and a small piece in y. So a very small piece in y would be 2 times x, the decrease or increase of x. And you say, oh, so that depends on x. Meaning, if I say x is 5, I will get a different dy than when x is 10. Here it didn't matter because the derivative of x was dx, so it was always 3. Every time you change x, you see here, that was trivial. But this one isn't trivial. Meaning, if dx is 0.01, I expect dy when x is 10. So x was 10 and it increased by a small bit, or even if it decreased by a small bit, we can do both. If dx is negative 0.01, we expect dy here to be what? The 0.01, which is dx, times x, which is a 10, so instead of 0.01, it becomes 0.1, times 2, I expect it to be zero point 0.2. And if it decreases by 0.01, times 10 is negative 0.1, times 2 is negative 0.2. Meaning, when x becomes 10.01, I expect y to be roughly 100.2, right? This increased by 0.01, so that increases by 0.2. And if x becomes 9.9, 99, I expect y to be 99.8. It decreases by zero point 0.2. So let's see what happens when the actual value of y. So meaning if x is really 10.01, what would y be? And you say, get the calculator. I say, no, I didn't teach you that when you go back to how to square large numbers. Remember? Okay, you say this is forget about the decimal, we can add it at the end, right? This is one more than 1,000. So do you remember how we did that? Okay. You do 1,002,001. So it's 100.2001. Very close to what we expected. But you know why? Because we picked dx to be zero point zero 0.01. If we make it 0.00001, this one would be thrown away very to the right down the road, right? So as we get closer and closer to 10, the increase will get closer and closer to zero point 0.2 or the decrease. So again, if x is 9.99, forget about the decimal place, I say y would be 998,001. 99.8001 again, the same. And if you make that 9.99999, this would be 99 point probably 9998 or whatever at the end. So that's the relationship. That's how you get a rate of one variable that is related to another variable. So let's take an example here. We say, suppose we have, uh, where's the compass? I had it here. I hope. It didn't fall. Oh, here it is. So let's say we have a sphere here or spherical, something like a balloon. And we are inflating it. And we are inflating it at a rate, so the inflation at a rate of zero point 0.2 cubic centimeter per second, meaning its volume increases by that much. How much does the radius increase, the rate of increase of a radius when, notice here I have to give you some kind of a value, like here I cannot say y equals x squared and the rate here is whatever, what is the increase in y? You say, oh, you have to tell me what is x. You give me the rate of increase as 2 times x, but you didn't give me a value for x. So how can I can give you a generic equation, but I cannot give you a specific number. So when r, for example, equals 5 centimeter, what is the rate of increase of r when currently it's 5 centimeters? Well, if you see that the zero point 0.2 cubic centimeter here is an increase in volume, and you know the volume of a sphere, hopefully you know that, the volume of a sphere is 4/3 pi r cubed. So you can see that if I take the derivatives, the left-hand side becomes dv, the right-hand side, the 4/3 pi is a constant. So you multiply that by the derivative of r cubed, which is 3r squared. So the 3 and the 3 cancel. So you get 4 pi r squared. Is that it? No, that's not correct. dr. Or if you prefer, since this is the rate with respect to time, that would be dt and that would be dt. So, because it's per second, so with respect to time, this rate increases at zero point 0.2 cubic centimeter per second. So that's why we did dt. And we want to find the rate of increase of the radius when the radius was 5. So the equation that I have is that the inflation rate, the dv dt was zero point 0.2 equals 4 pi, and we give a value of r to be 5, so this is 25 dr dt. So you get dr dt. Notice that this is 100 pi, so you say it's zero point 0.2 or 0.002 over pi or over 100 pi. So that is a very small value. Yeah, of course, the radius would increase very slightly. Zero point 0.2 divided by 100 pi. It's 6.37 times 10 to the negative 4 centimeter per second. Okay? Of course, very small. Now, if we, what is that? Let's take another example. Let's say uh, we have uh, let's say, where is the pencil? Okay. This is a floor. It's again a very common problem. And this is a wall. And we have some kind of steps here, stair or like steps. A ladder. And this ladder is 25 feet long. At a particular point, it was 7 feet away. The floor was it was 7 feet away from the wall. And let's say we can say that at this instant, somebody, you were up there and I want you to fall down. So I pushed. We started moving that at a rate, let's say, of two would be too much, right? Uh, let's make it 2 feet per second. It really doesn't matter. And we want to know how fast would the top slide down. So if this is x and that's y, what is dy dt? It's not going to be 2 also, right? It would be different. And every time that this goes more to the right, this will go down faster and faster. Do you see that? That if the ladder is, say if this angle is very small, it will start sliding slowly, but at one point it would fall down very fast. So that's why I need to know what is the rate when and the distance. I cannot solve this problem, or can I? What comes to your mind when I give you these two values? If you say Pythagoras jumps to your mind, then you would be right. I need to use the theory to find the height of the ladder. Without a lot of work, it's 24 feet. How do I know? I will let you know in a second. So I know that if this is x and this is y, I know that x squared plus y squared equals 25 squared or 625. It doesn't matter how much. Why doesn't it matter? Because I'm going to say, if I take the derivatives, this would be 2x dx. Okay, don't say 2x because we are not taking it with respect to x. We are taking just a small change. And this would be 2y dy equals 0. I can simplify by 2, and that becomes x dx equals y dy. And notice that if I'm taking the derivative with respect to time, I can always say this is dt. I want dy dt, right? So dy dt or y dy dt equals negative x dx dt, and dy dt equals negative x over y dx dt. Very simple algebra. X is 7, so negative 7. Y is 24 over 24. Dx dt is 2 feet per second. The 2 and the 24 is 12, so you get negative 7 over 12 feet per second. What does the negative sign mean? If this is the positive x and this is the positive y, it says it's moving down, of course. Okay? You cannot have a positive value. And of course, 7 12, if you want to write it in decimal, that would be negative 0.583. So much faster feet per second. It's going faster than, this is moving because that distance is more, well, in fact, uh, it's it's going slower, right? 0.583. It's exactly because this distance is more than that, and you are dividing the small by the big. So, but as it goes down more and more, the x would be larger and the y would be smaller. So you will be dividing x by y, and that ratio would get higher and higher. And you can see that it slide fast and fall to the floor. Quickly, something that has nothing to do with calculus, but I told you when I wanted to give quick quizzes, in college, excuse me, and the kids would be, well, they are not kids, but for me they are. And the kids were really behaving. So I say, I don't want to make it hard on them. Let me give them integer numbers in triangles or even in 3 dimensions, but that's maybe a story for a different day. So here's a quick thing for you. If you give me any odd number, I can construct a Pythagoras triangle where all 3 sides are integers. It's so easy. So I'm not going to ask you give me one, right? Okay. So let's say you tell me 5. Okay. I'm going to square it. So that's 25. And then I look at the two consecutive numbers that add up to 25, meaning add 1 and divide by 2, subtract 1 and divide by 2. You get 5, 12, 13. In our case, I made this 7, and I said 7 squared is 49, meaning 48 over 2, 50 over 2. So that's why I made that 25. And of course, I knew that the third one would be 24. And of course, if you multiply those by any constant, you get another bigger triangle. And it works and you say, okay, so nice. It works only when you have odd numbers. I say, nope. It also works when you have even number. What do you mean? Give me any even number. Let's say you give me 6. So if it's even, I'm not going to do the same thing. I'm going to divide it by 2, which is 3. Then square it. It's 9. Take one below, one above. You know that this is 3, 4, 5 times 2. What if you give me 8? I divide it by 2. It's 4. 4 square is 16, so 15 and 17. And you can construct quickly, uh, you know, triangles that are 90 right triangles with 3 sides that are uh, integer. You can find another problem if you want, or um, maybe that's enough because it's just basically the same idea. Usually, you get either some volume or area that increase. You can get a rectangle, and we say one of the sides increases at one rate, but keeping, say, the area constant or whatever. So whatever. So stuff like that. Some relations that you already know. You know that the area of a rectangle is base times height, for example, or the volume of a sphere, or uh, a right triangle. So you always have to have some kind of a piece of information that you apply and then take the derivative and solve for the unknown. So it's pretty straightforward. I'm going to stop here and then probably next time we'll go over another topic of differentiation, like maybe the chain rule. It's so easy, and I've seen many students struggle with that for no apparent reason. I don't know why. So maybe we'll do that next time, and then we'll take implicit differentiation. I want to go also over uh, more stuff what haven't we done? Parametric equations, and then we move to polar coordinates, polar integration, and stuff like that. So keep checking on this channel, and hopefully you will get stuff that are helpful to you in math. Thanks and have a great day.